In this video, I'd like to walk through review number 2 for the trigonometry test number 1 that's upcoming here soon. Before we get started with the actual review itself, I'd like to point out an outline of the test. Objectives that you should be able to complete without the use of a calculator would be the following. Determine the values of 6 trig functions, and if you look at Math Excel, you can access questions from section 1.1, 2.1 through 2.5, and 3.1 for extra practice on these style of questions. You should be able to solve a right triangle given a trig ratio, say sine of theta equals 2/5 or something like that. And again, these sections from Math Excel can be used for practice. You should be able to find exact values of trig expressions, maybe not the theta value itself, but the value of the trig expression or the inverse trig expression given side lengths or a coordinate in space. These sections in Math Excel should help. Lastly, you should be able to complete a unit circle with angle measures recorded in both radians and degrees, as well as the coordinates of each. And you should also identify where trig values will be positive in which quadrant. Now, this will not be timed on the test, but keep in mind that I've asked you to practice this, and you should be able to do this portion of the test in under 5 minutes. When you switch to the calculator permitted portion of the test, it'll look something like this, where you would use trigonometric functions to find the coordinates of a point on a unit circle, and we call these non-primary because these are not ones that you would have memorized with the unit circle. You should be able to find angles with the same trig values. So what I mean by that is, when does cosine of cosine of theta equal 1/2? There's more than one angle that satisfies this solution inside of a unit circle. And since you would be using a calculator most likely for this question, make sure that you understand how to get the calculator to provide the additional results. You should be able to compute with the use of a calculator values of inverse trig expressions. And again, these results are found essentially within the unit circle, but not at locations in the unit circle that we've got memorized or that we have memorized. And then lastly, you should be able to solve non-right triangles, those oblique triangles, and there are going to be 2 questions on that from this section in Math Excel. Bonus questions will exist on this test, at least one, and it would be an extension of concepts that we've covered in this class. Essentially, if you review all of these sections from Math Excel, our textbook, you'll find some challenging word problems or diagram problems there that might be sufficient for bonus level work on this particular test. Now, as far as the review today, let's talk about these test questions. We have to draw these angle measures relative to the initial side. So all of our initial sides or beginning of our angle measures exist on the positive x-axis. So one side of our angle always starts here at the positive x-axis. And then remember, we generally rotate counterclockwise. Positive angle measures are a counterclockwise rotation. So the 150-degree mark is about 30 degrees away from horizontal over here, and we located this position by rotating in this direction. That's what we are indicating here when we say indicate the direction. For part B, this is a negative 45-degree rotation, so instead of drawing the angle up here where 45 degrees normally sits, we must draw it down here below and indicate that this rotation was found in this direction. Or I should say the angle measure was found by rotating in this direction. Lastly, 600 degrees. Now this is greater than 360. It's greater than 1 revolution. So if we subtract 360, we get a result of 240, and you should be able to do this mentally without the use of a calculator. The 240-degree angle measure is a clockwise rotation, and we know where that exists inside the unit circle. That's 30 degrees off of 270 right here. If you wanted to subtract 360 again, you could. That result would be negative 120, and you might recognize that as a negative 120-degree angle, or a clockwise rotation from the beginning. Now, I'm not going to mark this angle with either of these two arches because, again, this one that I've just drawn is a positive 120 degree rotation. This one, I'm sorry, negative 120 degree rotation. This one is a positive 240 degree rotation, but neither one technically is the 600 degree rotation. So please keep in mind that a 600 degree rotation, since it is positive, is a counterclockwise rotation of more than one rotation around the unit circle. So we should really indicate that diagram like this. So if we start at x, positive x-axis, complete one rotation, and then another 240 degrees on top, that's what would land in this particular position. Now in these other examples, we are going to use an angle measure measured in radians instead of degrees, and we must find two angles, one positive and one negative, that are coterminal with 2 pi over 3. So it might be helpful to sketch a unit circle with the angle measure indicated. This is the location of 2 pi over 3. This is something we memorized from our unit circle. And we just have to define or decide which other angle measures land in this same position. Now, since the result is going to be positive and negative, that implies that we can continue an additional rotation around for our positive angle measure, and we can consider a clockwise rotation for the negative angle measure. So for our positive angle measure, in this case, we could take the 2 pi over 3 and add a rotation of 2 pi units. We're not using calculators on this portion of the class, or test, I should say. So it would be appropriate to convert 2 pi into 6 pi over 3 in this case so that we have a common denominator. And now we see that 8 pi over 3 is the same position with an additional rotation, and it is a positive value. Similarly, with the negative angle measure, if we subtract one rotation, or 6 pi over 3, that too will lead us to a position, to an object in the same position. This time the angle measure will be negative. Try number 3 on your own. Pause the video and resume playback in a moment to check your work. Again, by adding an additional rotation of 2 pi units, in this case in the form of 8 pi over 4, we can obtain a positive angle measure that's coterminal with pi over 4. And when we subtract 2 pi units, or 8 pi over 4, that leaves us with a negative angle measure, a clockwise rotation that lands in the same position. Try number 4 on your own. Resume playback in a moment to check your work. So using the same techniques as before, we can add 2 pi units or subtract 2 pi units to obtain our positive and negative coterminal angles. In this case, 2 pi was written in the form of 12 pi over 6, so that we had common denominators that could be added or subtracted with the other fractions. For question number 5, we must identify angles, we say in standard position because this is relative to the positive x-axis, in which quadrant that contain a positive tangent result but a negative sine result. Now again, by citing the phrase, all students take calculus, we can indicate which quadrants contain positive trigonometric ratios. So if I want to know when does tangent represent a positive angle measure, well, that occurs in either quadrant 1 or quadrant 3. All trig values are positive in quadrant 1. Tangent results are positive in quadrant 3. When we consider the sine function, now sine is positive in quadrant 1 and quadrant 2, but this question is asking about where sine is negative. So if it's positive in 1 and 2, then it must be negative in 4 and 3, and the only quadrant that is highlighted by both of those conditions is quadrant number 3. So the only time that a trigonometric result will have a positive tangent value and a negative sine value is if the angle measure falls in quadrant 3. And again, when we're talking about angles of or angles that are in standard position. We're talking about angles that begin here and now end somewhere in this position, anywhere in quadrant 3. Moving on. For angles in standard position, which quadrant would sine be calculated to be positive and cosine be negative? Go ahead and pause the video and resume playback in a moment to check your work. In this case, sine is positive in 1 and 2. Cosine is negative in 2 and 3 because cosine is positive in 1 and 4. Try number 7 on your own, please. Pause the video now and resume playback in a moment to check your work. Now, the cotangent function behaves just like the tangent function. So if you were struggling with this question, realize that cotangent is positive in the same position that tangent is positive. That occurs in quadrant 1 and 3, so therefore the quadrant where sine is negative and cotangent is positive is quadrant 3. For question number 8, find all theta values between 0 and 360 degrees that satisfy the following equation. When does cosine theta equal 1/2? Well, recall from our definition of the unit circle that the cosine value of an angle measure is equal to the x-coordinate on the unit circle. So this question is really asking where on the unit circle does x equal 1/2? Well, this position here, the last position before vertical in a counterclockwise rotation, as well as this position down here, the last spot before vertical on a clockwise rotation, both contain x-coordinates that are equal to 1/2. Now, the angle measure associated here is 60 degrees, whereas the angle measure here is 30 degrees beyond 270, or 300 degrees. So we can report this answer, theta, as 60 degrees and 300 degrees. And again, these two results are easy to obtain if you've got your unit circle memorized, which is expected in order to be prepared fully for this test. In number 9, we're asked a similar question. Where does sine theta equal negative radical 3 over 2? Well, again, sine theta is a discussion of the y-coordinate. So where inside our unit circle does the y-coordinate equal negative radical 3 over 2? That occurs at this position and this position. So the two angles that we're referencing here is 30 degrees less than 270 and 30 degrees more than 270. And we can report that answer, theta, as 240 degrees and 300 degrees. Now you'll notice that my answers are values between 0 and 360 because that's the way the question was worded. If the question was phrased differently, or if you were in a different situation, you might report these angles slightly different, maybe negative angle measures, or as some angle measure relative to another position. But this series of questions clearly does ask for our results relative to a unit circle between 0 and 360 degrees. So we are talking about the positive angle rotation to each of these positions. Number 10, we'll address the problem much the same way. We'll need a unit circle. And now we need to know, when does cotangent equal negative radical 3? Well, cotangent, you should recall, is the result of our x values divided by y values. And we would like to know, when does x, or when do the x coordinates divide by the y coordinates to equal negative radical 3. And sometimes it's helpful to recognize the opposite of radical 3 as a fraction over 1. Moreover, we might recognize, because radical 3 is not an x position on the unit circle, and 1 is not a position, well, it could be a position for y on the unit circle, but it doesn't happen in the same spot as radical 3 for the x value. What we do see as coordinates in our unit circle would be radical 3 over 2 and 1 over 2. These two coordinates occur simultaneously, and the fraction radical 3 over 2 over 1 over 2 would reduce back to negative square root of 3. Try to make that negative sign stand out. So where in the unit circle do we have an x value that's negative radical 3 while the y value is 1/2? Well, that occurs right here. We should also note that if I had a negative sign in the denominator of the fraction instead of the numerator, we could have a positive x value of radical 3 over 2 with a negative y value of 1/2, and that would be the position right here. And these two angle measures satisfy the criteria. This first angle is 30 degrees before horizontal, so we'll call theta 150 degrees. And this angle measured at the end here is 30 degrees before horizontal again, returning back to position 0. We can call that one 330 degrees. It's worth noting that the problem could be written in such a way that the angle measures should be reported between 0 and 2 pi radians. That doesn't change our approach, however, it just changes the way we report our results. For example, 150 degrees is the same as 5 pi over 6 radians, and 330 degrees is 11 pi over 6 radians. So if the instructions had been modified just a little bit, then our answer would be modified a little bit as well. In this case, the blue answer is correct for the original problem, and the gray answer is correct for the secondary write-up. So let's switch to the calculator permitted portion of this review. And we should be able to find the coordinates of the point P on this unit circle. We should recognize that while we're looking for x and y coordinates, those are simply computed by using cosine and sine, respectively, to compute x and y. So if I compute cosine of 250 degrees and sine of 250 degrees, then the calculated result will provide the x and y coordinates of this position. Now, based on the limitations of our calculators, it is possible that the symbol or the sign that's produced as a result is not the correct one, and we would have to interpret that as we go. Certainly what we're looking for is an x value that's negative and a y value that's negative to land at this position on the unit circle. So let's see what the calculator produces. We'll start with cosine. Cosine of 250 degrees is, let's press Control Enter for an exact result, is negative 0.34. That's good. Negative 0.3420. That's to be expected. And that seems reasonable. The x coordinate in this position appears to be 0.3 units to the left of the origin. When we compute sine, we also get a negative result, 0.9397. Which is good to see as well, because this does also look like a negative 0.9. It's very close to negative 1 on the y-axis. So there's no need to adjust the x and y coordinates here. These two numerical values are exactly what we would expect to see, negative on both accounts. So if we were still working on a position inside the unit circle, between 0 and 360 degrees that is, could we find another angle measure that has the same sine value as the angle measure 250 degrees? Well, remember, and this goes along with what I was saying back here, there is another position, and potentially a result off of our calculator if we're not careful, that meets the same criteria as the sine of 250, but it might end up in a different position. So sine of 250 is the y coordinate associated with 250 degrees. That's also going to occur right over here. And so this angle measure, relative to positive x, would also have the same sine value computation. Now, it's easy to find that angle measure. We know that 250 degrees is just 20 degrees away from this vertical. So this angle measure on the right side is also 20 degrees off of that vertical. It's just 20 degrees beyond. So find the angle measure with the same sine as 250. Well, that would occur at the angle 270 degrees. For cosine, we have a similar approach. The x coordinate was 0.3, And so an object or an angle measure that has the same x-coordinate would have landed up here on our unit circle in this position. So the angle measure here relative to the positive x-axis would also have the same cosine as 250 degrees. Now to compute this one, we could think of 20 degrees off of this vertical, much like we saw down below, or 70 degrees above this horizontal, just like this one is 70 degrees below the horizontal. There's a whole variety of different methods that you can use. In any event, we can make the claim that theta is going to be 110 degrees in this case. And since you have a calculator in front of you, you can check your work. I don't think you would use a calculator to solve it, but you can check your work. If I evaluate cosine at 110 degrees, we should see negative 0.34, just like we had cosine at 250 degrees. If I evaluate sine at 270 degrees, we should see the same result that we got, whoops, not 270. I think my math was wrong, wasn't it? 20 degrees beyond 250 was actually 290. It was a good thing I checked, huh? So now, let's verify this one more time. Sine of 270 should give us the same result that we saw at sine of 250. So again, hopefully some of you were screaming at the computer screen when you saw my mistake a few moments ago. It's a good thing I checked because now I caught that mistake and have made the correction. 20 degrees beyond 270 was 290. Lastly, where is an angle measure that contains the same tangent as 250? Well, hopefully by now you're seeing the pattern, or maybe you've recognized the pattern all along. When we evaluate tangent at this position, our result's going to be positive. I know that because this angle falls in the third quadrant. The only other position that's going to produce a positive tangent result is going to occur somewhere up here in the first quadrant. And if tangent is described as y over x, tangent of theta equals y over x. In this case, down below, we had a negative y value and a negative x value, which is exactly the same as a positive y value divided by a positive x value. So if I took the coordinate here and used the positive x form and the positive y form, that would place a position or angle measure right here. So one more time, we're 20 degrees off of vertical, 20 degrees less than 90, should put us at a theta value of 70 degrees. And when I use my calculator to check, you can see that tangent of 70 degrees is 2.7, and tangent of 250 is also the same, 2.7474. So I think that does a nice job of completing that question. Now we've got some word problems to encounter. So we have an interesting situation here. A row of 8-foot-long solar panels are to be inclined at 30 degrees and arranged based on this diagram down below. We would like to know the spacing x between each panel so that they will not cast shadow on each other when the angle of inclination, or the angle of the sun above horizontal, is 45 degrees. So you can imagine we've got the sun that's shining up here, and apparently this is the optimal position. We don't want the shadows from one panel to be cast onto the other at any time when the sunlight is at 45 degrees, because then that would obliterate the potential for sunlight or solar panel operation at this position. So basically what's happening here is we are creating oblique triangles, or a series of oblique triangles based on the sunlight that's being cast. This diagram isn't quite perfect, but we'll go with this shot here. So we know that above horizontal, we've got a 45-degree angle here. And because alternate interior angles are congruent, we've got a 30-degree angle here. And with that, or with those two pieces of information, we can determine that this angle is 105 degrees. And that's particularly important for us because in any triangle, whether it's a right triangle or oblique triangle, we must have 3 of the 6 components known, one of which is a side length. And we have that now. We've got an angle measure, a side length, and another angle measure. So with my triangle identified, I will go ahead and list the components of this triangle. We have side lengths and angle measures. So the angle measures, capital A, B, and C, and the side lengths A, B, and C, using lowercase letters. It appears that angle C is 105 degrees. Side length C is the unknown. That's what we're looking for. We have angle measure B, which is 30 degrees, and side length B is unknown, but not really part of this problem. We're not interested in side length B. Side length A is known at 8 feet, and it would be necessary to have angle A in order to use the law of sine, so let's go ahead and compute that. That's easy to do. The sum of our three angle measures must be 180 degrees. These two add to 135, so an angle measure of 45 degrees would be sufficient to make the sum 180. So this angle measure is 45 degrees at this position. Now that I have two components that are opposite of one another, I can set up the law of sines. Sine 45 divided by 8 must be equal to sine 105 divided by x. We're going to use this pair down here because ultimately we're looking for the distance between the bases of each of these solar panels. And you should recall that the process for solving for x, the unknown in this position, is to choose the two values that are diagonal, not including this value, so the diagonal numerical values, multiply them together, then divide by the third result, which I've shown here in this setup, 8 times sine of 105 divided by sine of 45, and that will always equal the result in this denominator, or this position here, the fourth position. X is already isolated, so when I compute the result, we see that that distance is 10.9282 feet. 10.9282 feet. And that seems appropriate. If the panels are 8 feet long, then the spacing is going to be close to 11 feet, and that seems pretty realistic according to this diagram. Let's try our last example. An upright 50-meter tall radio antenna is to be built on a hill that makes an angle of 5 degrees with the horizontal, and that's indicated in the figure below. In order to stabilize the antenna, guy wires are attached at the top and secured to the ground. Calculate the length of each guy wire. So we're looking for essentially this length, and we have ourselves a non-right triangle that's formed. If we could calculate the proper components to this triangle, then certainly we can solve the triangle and determine lengths x and y. Now I'm going to use our typical naming scheme where a, b, and c represent angles, and lowercase a, b, and c represent side lengths. I'll make a quick note here that side length c is the sum of these two distances, 30 and 30 meters. So we'll call this a total of 60. Although the more I look at this diagram, I don't know that that's going to be all that helpful. If we look at this entire triangle on the outer edges, we certainly have one side length, but we don't have any other information. This 50-meter measurement is the height of the tower. It is not associated with the original triangle whatsoever. In and of itself, that's not a problem. The 5-degree angle that's provided, however, gives us 5 degrees relative to horizontal. It does not specify the angle measure inside the triangle either. So I think a slightly different approach would be better. Let's imagine two triangles that are formed here, and we'll separate them down this vertical line. Now, if I look at the triangle on the left, in fact, I'll use a different color to make this stand out. I have two side lengths that are provided, 30 meters and 50 meters, and all I would need is an additional either side length or angle measure. Well, I don't have the side length because that's what I'm looking for. All I need is an angle measure. And again, we noted a minute ago that this angle measure can't be found because the provided information gives us the angle measure relative to horizontal. It doesn't describe the angle of the guy wire. But that measurement relative to horizontal is helpful to us in this regard. Here we have a 5-degree angle, and therefore we would also have 5-degree angle here. vertical angles are congruent. Now we're also being told that the tower itself is upright. It's perfectly upright. So that means that it's 90 degrees to horizontal. With that being known, it should be clear now that this particular angle is 90 degrees plus 5 degrees, or 95 degrees. And now we have an SAS triangle that can be solved by using the law of cosines. And if we'd like to relabel this, we can solve, or we can claim that this angle measure is A, this angle is B, and this angle is C. Therefore, the side length that we're going after is side length B. In a similar sense, we could solve the triangle on the right-hand side. I'll mark it with a different color again. Again, we have a side length here and here. The angle measure in between now can be found at 85 degrees because the sum of these two must be 100. Similarly, it's 5 degrees less than a 90-degree angle. And now that triangle can be solved as well. This is an SAS, law of cosine situation again. So since these two are similar, I think what I'll do to solve for x and y is just to set up the expression for the law of cosines that allows me to solve for the side length that's opposite of the provided angle measure. At this point in class, you should have had enough practice to do this, and you also have your formulas available for reference on this test. So I certainly think that this setup is reasonable for you as well. X squared is going to be equal to the sum of the other two side lengths squared, so 30 squared and 50 squared, minus 2 times those two side lengths, 30 and 50, times cosine of the angle measure that is opposite of the side length that we're going after. We should also note that if x squared is equal to this expression, then x by itself is equal to the square root of that expression. So that's something that I can reach for the calculator to compute. Before I do that, however, I would like to point out that y is computed in much the same way. Y would be equal to, again, conferring the same diagram, we've got two side lengths, 30 and 50, with an angle measure of 85 this time. So the expression is going to be virtually identical. 30 squared and 50 squared, less 2 times 30, 50, and the cosine of 85 degrees. And those two computations will allow us to calculate x and y. And here are the two results generated by the calculator. One measures 60.51 feet, so the larger is 60.51 feet, and the other is 56.0226 feet, or 0.0226 feet. Sorry, the side lengths here are actually meters. Hope this video helps see the understanding of the applications of the processes that we've worked on so far. If you have further questions, please let me know. You can send me a message through Schoology or an email directly, and I'll try my best to answer them as soon as I can. Thanks for watching.